Okay, we are starting the afternoon session. The next speaker is Professor Erland Schulson from Dartmouth College, and he's talking about the rapid healing of thermal cracks in ice. Erland, you can start your talk.
Well, thank you very much. And thank you for your being present there. I'm here in Hanover, New Hampshire, 10:30 in the morning. And this is the first time I've participated in a conference in this mode. I hope it will work out and we'll be able to understand each other as well as I can. So let's begin. And I begin by pointing out something everybody knows, that all solids are vulnerable to thermal cracking and to the degradation of mechanical behavior that results from the defects that are so created. Well, this is a story about ice. And we call it the rapid healing of thermal cracks in ice. And we're going to find that the cracks, although initially form, don't stay around very long. And so with me in my office at Thayer, Dartmouth College, is my co-worker, Dr. Andre Merzda. And so he will be listening as we go forward and he'll correct any mistakes that I make. So with that, let's continue and move forward. Just trying to get this screen to move. Oh, okay. So there we are. So I point out that in ice, in particular, that the occurrence of thermal cracks is fairly well recognized. And it happens when the temperature of the air falls relatively quickly below the temperature of the water below, such that the differential thermal contraction that results leads to the development of tension and tensile stresses in the upper layers, which tend to relax through the development of cracks, particularly when the rate of change of temperature is fast enough. If it's slow, creep deformation relaxes the stresses, they don't develop. But if the temperature drops quickly enough, then stresses build up to the point that the stresses relax through the initiation of cracks. This we know. And here's an example of thermal cracks in a sheet of ice, if you wish. Now, I'm not putting the scale on because generally they can be of various sizes. But the character of thermal cracks is really they're randomly oriented within the body. And that random orientation really is a signature of their origination from thermal contraction and not from the development out of some applied external state of stress. They vary in length, small ones, sub-meters, even down to the millimeter, to large ones, hundreds of meters. And in depth, that too varies, all the way from through the thickness of the ice cover to only partway through the thickness, if you wish. Their action on mechanical properties is to initially concentrate stress that will develop from the action of wind and ocean currents, that is, from the stresses that build up through an applied load on the body. And that the cracks, the ones that are preferentially oriented with respect to the global stress state, they can lead to the localized buildup of tension at crack tips. They can slide cracks that are locally oriented with respect to a compressive state of stress. And that tension that develops, if it's not allowed to relax through creep, that is, if the stress is applied rapidly, so that the stress at the crack tips is rising rapidly, then it can relax again through the initiation of cracks. And those cracks can become rather large, and in the end, depending upon the state of stress, whether tensile or compressive, can lead to failure of the ice sheet. And this is just a schematic sketch of, for example, a kind of failure that might happen under a multi-axial state of compression, where faults occur. They've been referred to as linear kinematic features. I've referred to them as conjugate shear faults that develop within the ice cover under a compressive stress state, as long as the confinement is not too large. These through thickness thermal cracks, we know, can fill with water, that is external water, and over time that water can freeze, and rendering such cracks relatively ineffective in concentrating stress. We tend not to worry about them. But I would ask, and this is the subject of this paper, what about dry, in quotation, dry cracks? What's their role in the structural integrity of an ice cover? But they contribute to the eventual breakup, say by reducing flexural strength or by increasing the propensity for fatigue under the flexing action of oceanic waves. So it was with those questions in mind that we performed some experiments in the laboratory, some experiments on the flexural strength, rather, of dry thermally cracked ice. And I know those who are more familiar with the field than the laboratory may think, well, forget about the lab. That's not the field, for heaven's sake. And in defense, I would argue that it's only in the laboratory that one is able to separate systematically the factors that could be at play in any phenomenon. The question then, in having separated them, as you'll see here, is having understood the factors, how then do we apply it to the larger scale? I'll say a few words about that later. I'll tell you the principal findings straight up front, that the cracks we introduced into ice, and I'll show you the ice, weaken the ice initially, but not for long. The cracks heal within matters of seconds, tens of seconds, hundreds of seconds. And as a result, the flexural strength is completely recovered, no change. That was a surprise to us, but let me explain to you and show you the results, and then we'll go forward. So the work I'm describing was just published just recently in Geophysical Research Letters, August 24th edition, and here is the reference if you wish to look it up. So everything I will be saying, or much of what I'll be saying, is in this paper. So here's the experiment. We prepared or examined the behavior of three kinds of columnar grained ice. This is the kind of ice that characterizes most of the Arctic sea ice cover. And indeed, the character is such that the crystallographic c-axis tends to be confined to the horizontal plane and to be randomly oriented within that plane. And that ice has been designated all the way back from Bernie Michel to S2 secondary ice. And I show you a wolf net on the side here, the upper right-hand side, showing the orientation of the c-axis as you look down on the ice sheet, a bird's eye view, and you see they're randomly oriented. And the three kinds of ices that we studied, shown in figures A, B, and C, all columnar grained. We see a vertical orientation and a horizontal orientation in those those images. Three kinds of ice. First year sea ice for one, that is ice that was harvested from the Arctic Ocean. Secondly, saline ice, the kind that we actually grew in our laboratory. And the third one is freshwater ice, that is salt-free ice, also that we grew in the laboratory. And you see the character, the density, the column, the meltwater salinity. They're about the same except for the salt-free ice. And we took beams of materials of that kind. We took beams, relatively small beams, and I've indicated the dimensions of the beams on the lower right-hand side of your image. I hope you can see it. They're about 300 millimeters in length, 75 millimeters in width, and 13 millimeters in thickness. And those beams were loaded in 4-point loading using a device we built. And you see the loading system in that image. And to begin, before we did anything, we measured the flexural strength of the pristine material. And that strength, you'll see, is listed in the table, the lower table in this image, as well as the strengths and their standard deviations. You'll see the temperature, and we explored the range of temperature from -3 centigrade to -78 degrees centigrade to get a good range, and you'll see why in a moment. And so that's the experiment. Loading in 4-point loading, the principal stress, that is the maximum tensile strength, acted in a direction across the long axis of the columns, just as it would in a natural sea ice cover. And so we're trying to simulate as best we can in the laboratory the natural loading scenario. So let's move on and see what we found. We shocked the ice. The thermal shock was obtained by spraying the surface with liquid nitrogen. We also tried spraying the surface with a cold medical spray, same effect. And as well, we shocked the surface by putting a cold metallic plate on the ice, same result. So the results that I'm going to show you do not depend upon the method with which we use to shock the ice, to put in the cracks. So here we have two images, saltwater ice on the right, or saline ice. It's actually the sea ice. And on the left, freshwater ice. And you're seeing it as it was, just as it was shocked. A narrow spray, not much wider than that network of cracks that you're seeing, was placed on the ice, and boom, cracks came in. You can see them clearly in the freshwater ice, not so clearly in the saline of the sea ice, because of course that material is much more optically opaque owing to the presence of the brine pockets. You know that, but I think if you look closely, I can see it on my screen. I hope you can see in that central region, that same kind of pattern of randomly oriented cracks. I hope you can see that. Well, this is what happens when you load the body. And now I will show you results first from freshwater ice. And the image on the left is the one you just saw. The image in the center is of the ice as it was broken immediately after being shocked. And you can see where the crack went. The fracture is shown by the blue arrow, and it runs right across the center of the cracked pattern. That's what you would expect. That's what we expected. But if you, before loading after shocking, just allow the ice to sit around for a while, things are different. And the image on the right, the ice was allowed to sit for about 5 minutes, 300 seconds. And then it was broken. And now you see where the fracture is. It's gone not through the pre-cracked area. Instead, it's gone into the pristine ice. And that is a reproducible result. You see remnants, if you wish, of the cracks that previously existed, but those are, we call them scars. There's some evidence of the pre-existing crack, but it's not doing anything to impede the mechanical property. There's just perhaps some air entrapped in the old spaces. We can talk about that later. But there we have it. The fractured region, the initially thermally shocked region, given a little time to heal, was no longer a weakening element. Let's look at the saltwater ice. Same story. You've seen the image on the left before. Here now in the center is the ice that is being broken immediately after being shocked. And yes, fracture again went right through the region where the cracking cracks had been imparted. No surprise. But now this time, let it sit around. In this case, only half a minute. And look where the fracture went this time. Again, in through the pristine material. Well, this did surprise us, I have to admit. But we decided to try and understand this more and perform some quantitative measurements. But before I do it, let me show you what I call a Faraday, Michael Faraday, 1860 kind of experiment. You may all remember that back then, Michael Faraday taught us that if you took two pieces of ice, stuck them together or pushed them together, they stick, they bond. So what we did was we took a piece of ice and we scratched the surface. You can see the scratch in the surface. And I'll turn on this video in hopes that it'll play for you. So we put a scratch in the surface in the lab and we broke it. And then we pushed the pieces together. Minus 28, they stick. They in fact have bonded. Now, certainly a fracture surface is much rougher than is a surface created through thermal cracking. And so one expects that the degree of registry or from one side to the other, the contact is not as good, but yet it still did contact, and we see evidence of rather rapid healing. Okay, for the quantification of this observation and this effect, first I'll show you the results of freshwater ice, and then I'll show you results from sea ice and the saline ice that we prepared in the laboratory. So again, this is freshwater ice, columnar grained, S2 type crystallography. That is, the c-axis is in the horizontal plane as in nature, and the ice is being loaded across the column, being bent in 4-point bending. And what's plotted here is flexural strength on the ordinate and the time of healing or time of annealing or what you wish on the abscissa. The flexural strength in this depiction is normalized. That is, it's the strength of the ice as cracked divided by the strength of the ice initially, the pristine strength. And so what you see here as a function of time is an increase in the strength. That is, at close to zero time, about a second or so, the strength is about half of what it was in the pristine state. Wait for a while, and we find this, oops, I have to go back, sorry. Wait for a while, and you see the strength increases, and by about 300 seconds in the freshwater ice, the strength has recovered completely. The little numbers under each of the points indicate the number of tests that were done, and we ran about 130 tests, indicate the number of tests that were done under each condition. Sure, there's scatter, but the trend is very clear. As you wait for a while, the flexural strength recovers, and if you wait long enough, it recovers completely. Shown here a set of data from -3 to -28. Let's now go to the saline ice and the freshwater ice. I mean, the saline ice and the first year sea ice. Again, we're plotting the same normalized flexural strength versus the time. And we see that immediately upon shocking, or relatively immediately, the strength is down about a factor of 2. No surprise. But again, allow time to pass and the strength begins to recover. Now, it's very clear in this image that the recovery does increase with an increase, the rate of recovery, to put it the other way around, it'll be negative. The rate of recovery decreases as we decrease temperature. That's very clear here. Note the blue points were obtained at -78 centigrade, and the red and the green at a higher temperature, and the black too, at a higher temperature. But I think you can see that there clearly is an effect of temperature on the kinetics of the recovery process. Message again then, it doesn't matter which kind of ice one is allowing to heal, or rather to crack and then heal, healing will occur. Well, to illustrate what we're seeing, here is a case of sea ice, and you're looking at the ice as it was harvested, or a piece of the ice as it was harvested from the Arctic. And again, I'm going to show you a video of what happened. Now, what you'll see in the video is how the ice was sprayed. And what I want you to pay particular attention to is how very rapidly these cracks actually disappear from the field of view. And this is at -10 centigrade, so the ice is darn warm. Here we're spraying. There's the liquid nitrogen that's going onto the sea. You can see the cracks, but they don't stay very long. And notice this ice was being sprayed as it was being loaded. Notice where the fracture went, outside the sprayed zone. So saltwater ice is healing very rapidly. So let's go back. I want to go back. So let's look at this result. First, I'm going to say freshwater ice. Healing, let's say at -10, 300 seconds, okay? Job is done. Let's go to saltwater ice. Here it is. Whether it's saline ice or ice that we grew in the laboratory, that is the red, green, and black points. Notice, not in 300 seconds, 30 seconds is completely recovered. If you drop the temperature to -78, well, it's going to take longer. It's looking, 300, 400, somewhere there. So this is interesting, that the presence of salinity actually enhances the healing kinetics. So what's going on? Well, firstly, about the strength of the ice as cracked, that is, no time was allowed. Well, fracture mechanics teaches that if the cracks are large enough and the stress is high enough, that the stress intensity factor will be critical, the cracks will propagate. And so if we put in the depth of the crack and their length, and we work out the stress intensity factor at fracture, then we get a value of 89 plus or minus 18 kPa root meters. Now, that's a fairly wide variation, but it's totally consistent with independent measurements of the fracture toughness of ice. And the fracture toughness of ice does not change much with temperature, nor does it change much with salinity, at least within the detectable limits of experiments and the plus and minus uncertainty in those limits. So it's a pretty robust number, if you wish. 100 kPa root meter is one I typically use, 89 kPa plus or minus, it's in that ballpark. So we're happy that the ice, as cracked, obeys the dictates of fracture mechanics, but not so of ice that has been allowed to heal. And so to try and get some insight into the healing mechanism, the kinetics, we just took the data. Now the data are scattered. So to be as objective as possible in our analysis, we assumed there'd be Arrhenius behavior. And we assumed as well that the rate of recovery could be functionalized through this expression you see here. No physics is intended. This is just an expression of the data as they occurred. And you see them on the lower images, how they obey, and they kind of look like that equation. Well, what's important here is this healing time, this time to heal, that is to get back to the strength of the pristine ice. That healing time we take to be a characteristic of the mechanism. And if we plot the reciprocal of that healing time, taking it to be a measure of the rate of healing, and plot that as the reciprocal of absolute temperature in an Arrhenius manner, we can get an activation energy. Now, as you see here, we don't have many temperatures. For the freshwater ice, the temperature, we only went down from -3 to -28, not big enough, and there was enough scatter. And so the blue curve, well, it's not very steep, and it leaves us the blue curve an energy of about 10 plus or minus 12 kilojoules, but that's a big range. Look at the green curve, that's for the saline ice and the sea ice. It's steeper and the data are better. And so from the saline or sea ice, we get an energy of 28 kilojoules per meter, plus or minus 7. Well, in checking through the literature, we found that the energy of self-diffusion, the activation energy for self-diffusion in ice, 23 kilojoules per mole. The energy for volume diffusion, more than twice that, 60 kilojoules per mole. And so we're struck by the similarity in the energy for self-diffusion and the activation energy for this healing process. We think, therefore, that what's going on is a sintering kind of process. That healing appears to be a thermally activated process, sintering, that upon warming, after thermal shocking, the opposing faces of the cracks, they come together, and then they sinter via surface diffusion, thereby forming new atomic bonds across the interface. Consistent with this role of thermal and surface diffusion, we would say, is the positive effect of salinity in increasing the rate of healing. You see, upon cracking, brine is expected to escape from some of the pores within the warmer saltwater and freshwater and saline ice. And upon escaping, the brine wets the surrounding surface and increases its effective thickness of that liquid through which the diffusion occurs. So we would argue that this wetting-induced enhancement of diffusion increases the rate of sintering, and that is in keeping with sintering theory. I'll give you a reference to Swinkles and Ashby on that subject. In addition, we say healing may be assisted, probably is assisted, particularly within the freshwater ice, by the presence on the crack faces of a quasi-liquid layer. Now that quasi-liquid layer has been revealed through experiment and theory, indicated references for you here. And although it's possibly discontinuous along our crack faces, it's nevertheless in contact here and there in the other place. And that layer has been invoked to account for the subsecond sintering of icy needles, push them together under zero load. And as well, I go back to Faraday for the rapid joining together of pieces of ice when placed in contact. So that's what we think is going on. But now back to the ice cover. Let's see, we have to go back to the sea ice cover since that was our focus in the first place. So we ask, what about the possible contributions of cycling, thermal cycling, come cracking, come flexing through wave-induced action on the ocean. Now, typically the frequency of waves may be 0.1 hertz, that is 10 seconds about for a period. Well, that period is pretty well similar to the period of cycling, or the time it took for our warmer saltwater ice to heal. If you look through about 10 seconds, it was pretty well healed. So we would say, well, should behavior on the large scale reflect the behavior on the small scale, then the tendency for thermal cracks to heal rapidly, that is dry thermal cracks, would we think limit their effectiveness as stress concentrators. And this could offer some defense against loss of structural integrity through the creation of dry cracks. Now, whether such cracks introduced into the sea cover also heal rapidly, it does require further work, and that's what we have in mind to do. Well, that's my story, and thank you for your attention.
Thank you very much for the talk. Any question from the audience? Eli.
Hi, thank you for your presentation. I was wondering if there would be any difference if the ice plate was laying on saline water while it was loaded, so that the water could have filled the tiny cracks, maybe.
Well, of course, because they would be through thickness cracks. And as I mentioned earlier, cracks that run all the way through are wetted, and that wetting eventually freezes. And in time, they have no effect at all, we expect. But if they do not go all the way through, then I expect they might still act as stress concentrators and weak material. But they could heal. But we intend to find that out.
Hello. I was wondering if you did some other tests in shear or convergence. Do you expect the results to be different?
I suppose one could put pure shear on a plane in the ice cover by pulling it in tension and compressing it at the same time, at the same level of stress. And that would create a plane on which there was pure shear and no normal stress. Now, how that would behave, I expect it would just crack, because the tensile stress would crack it. If there are cracks in the ice, regardless of how they originate, and if those cracks remain dry, and if they are allowed to come together in contact, perhaps under a mechanical load as well, then they may have a tendency, indeed they do have a tendency to heal, because you saw the example in that video of our having broken apart two pieces of ice and stuck them together. They did stick. Admittedly, the strength probably wasn't very great, but at least they did stick at some points along the interface, along the crack surface.
Okay, we have a question online from Alexei Marchenko. Thanks for the presentation, Erland. Did you check the air humidity in the lab depending on the temperature?
The humidity in the laboratory, depending upon temperature, we did not make that measurement, not particularly, no.
Okay, thank you very much for your answer. Thank you very much for the presentation. Do we have any other question here? No, thank you very much, Erland, for your presentation, and we can move on to the next presentation. Can you stop sharing the presentation on your side?
I will do that.